We're now going to look at a skill that shows up from time to time and sometimes presents a bit of a challenge. Find a vector function that represents the curve of intersection of the two surfaces, one of which is the cylinder x squared plus y squared is equal to 4, and the other is the surface z is equal to xy. We have a good idea of what the cylinder looks like. We may or may not know what z equals xy looks like, but knowing what it looks like is irrelevant for our task right now. We just want a vector function that represents the curve of intersection. Another way to put this is we want to parameterize the curve. It can be difficult to know where to kind of start the attack plan here. I'm going to start with the cylinder x squared plus y squared equals 4, because to parameterize that, if we let x equal 2 times the cosine of t and y equal 2 times the sine of t, that represents a circle of radius 2, and now we just need to deal with the z portion of it. But if we've let x equal 2 times the cosine of t and y equal 2 times the sine of t, and if x is the product, if z is the product of x and y, then z is going to equal 2 times the cosine of t times 2 times the sine of t. We can express this as 4 times the sine of t times the cosine of t. And then to just make things a little bit nicer, we can actually use a double angle formula and say that this is 2 times the sine of 2t. Our vector function then, and so we've just written the parameterization, right? We have x, y, and z in terms of t, but we were asked for a vector function. And so I need to package this as a vector function. And our vector function is going to look like r of t is equal to 2 times the cosine of t, 2 times the sine of t, 2 times the sine of 2t. There's our vector function. Now, that's not the only way to do it. We can look at an alternative method. And I've rewritten our surfaces just to have them in front of us. For the alternative method, sometimes it's useful just to say let x equal t, right? Let one of the variables be our parameter. And if that's true, then that would imply that t squared plus y squared is equal to 4. I don't know what I just drew there. It should look like a y. And if that's true, then y squared is equal to y squared is equal to 4 minus t squared. Got a little ahead of myself there. Which would mean that y is equal to either positive or negative square root of 4 minus t squared. We just square rooted both sides of an equation, so we need to remember plus or minus. Well, this time we have x equals t, and x is showing up in z equals xy. And we have y is one of two radicals, but it's still showing up in xy. So we're going to have to actually write down two functions. So I'll say r1 of t is equal to t, the positive square root of 4 minus t squared, and then the product of the two, t times the square root of 4 minus t squared. And r2 of t is equal to t, the negative square root of 4 minus t squared, and then negative t times the square root of 4 minus t squared. Now, I'm just thinking that this is a valid representation for the curve, but I don't think that we actually follow the directions here because we were asked to find a vector function that represents the curve of intersection. What we did with the sine and cosine is a vector function. This is actually two separate vector functions, but they do represent the same curve. I'm going to call the one with the sine and cosine the actual answer. Now let's see how we can use a graphing utility to represent this curve of intersection. GeoGebra has a 3D graphing tool. You can find it by Googling GeoGebra 3D graphing tool, or there's a Canvas module for it, or it's on my website as well. In order to enter a vector function, we type in the parametric equations as though we're typing in an ordered triple. So I'm starting with parentheses here, and x is equal to 2 times the cosine of t, so there it is. Y is equal to 2 times the sine of t, and then z is equal, oops, I didn't even mean to type z. Z is equal to 2 times the sine of, and I'm going to put parentheses around the argument, 2t. And what we see here is this, well, it's cut off a little bit, so let me zoom out. And it looks like, I don't know, a hoop earring that somebody really had a bad day with. Anyway, it's, well, it's the curve of intersection. To see how this is the curve of intersection, let's go ahead and graph the surfaces. To graph the surfaces, we just type in the equations the way they appeared. We had x squared plus y squared is equal to 4. And so what we see is that this sadly shaped hoop earring here, it exists on the cylinder. In fact, from above, it's just a circle. And it gets its shape because of it's the intersection between that cylinder and the surface z equals xy. And whoa, that went a little weird on us. Let's zoom out a little bit, and I'm going to actually fix the colors here. And when I say fix, I really just mean give you some contrast there. So now we see this hyperboloid of one sheet. I don't know, it looks kind of hyperbolic to me. In fact, we're going to see how this is related to hyperbolas in a later section. But when this hyperbolic thing intersects the cylinder, it does so along that black, sadly shaped hoop earring curve. And so what we parameterized is that curve of intersection. I'm just showing this to you for a few reasons. One is so that you can see how we enter things into GeoGebra. And notice it added a bunch of stuff, curve, and it's probably got parameter values for t. T goes from 0 to 2 pi, all that. It added all of that. But then also so you can see how we can represent equations. And finally, to convince you that what we just did works.